Hello and welcome back to Data Science for Humans. Today we're looking at OLS regressions using Python. Ready to rock and roll? So am I. Let's talk about what these things are. So what is an ordinary least squares, or OLS, regression model? Well, these estimate relationships between one or more independent variables and a dependent variable. Our goal is to have some sort of graph that predicts the value of our dependent variable based on all of our independent variables. In OLS, we're interested in minimizing the difference between the observed values, so the actual values that we see, and the values that are fitted to the line. So we want to basically fit a line that goes between all of these values and minimize the distance between the line and every single value. So in English, what does that mean? We minimize the distance between our line and our data points. An observed value is a specific data point. For example, when unemployment is equal to 5%, crime is equal to 27. So that is a data point. And a fitted value means what is the data that would be predicted on the line. For example, when unemployment equals 5%, the predicted value on the line would be 23. There is a fantastic website where you can play around with ordinary least squares regressions at Sedosa.io. This will be linked in the video description below. This ordinary least squares regression simulation by the Sedosa.io website. This has been written by Powell and Lehe. This is a fantastic way to visualize and play around with what ordinary least squares look like. So check this out. On this webpage, and I'll zoom in a little bit, on this webpage we can see that we have a graph, and see this line? This is our OLS regression line. Our objective when we're creating our OLS model is to have the model create this line where the distance between the points, our observed values, and the fitted values, the value on the line, is minimized. Notice as one of these values moves around, the position of our line moves around. So check that out. That line is responding to where that point lies. So all of these points in purple, all these points that are off of the line, these are our observed values. In this case, what they're demonstrating is hand size versus height. So in other words, based on a specific hand size, we're trying to figure out what your height would be. So check this out. Notice that if I move one of these values down here, for example, I have a massive outlier that can actually tweak the line quite a bit. So, again, a linear regression example, we have our independent variable x and we have our dependent variable or response variable y. And we're trying to fit a line between all of these points. And this will actually give us a regression line. So you can plug in a specific value of x to get your predicted value of y. We're going to make a few critical assumptions. Three of the most important ones are that the relationships between our dependent and independent variables are linear. Our second assumption is that we have few, if no, outliers in the dependent data. So in other words, we're going to somehow control for the outliers that we may have in our dependent observed values. And finally, the variability in our dependent variable is equal across all values. What does that mean? We'll take a look at that third one in a second. It's a little bit tricky to wrap your head around at first. Let's look at our first assumption, that our relationships are linear. So for an ordinary least squares regression, linear regression, we're making the assumption that as our x value increases or decreases, our y value should generally increase or decrease. That will give us an accurate prediction. So notice on the left-hand graph, we have a linear relationship between our independent variable and our response variable. So as our independent variable increases, our dependent variable seems to increase as well. On the right, we see that we have more of a parabolic relationship. And so this line doesn't really give us a good predicted value. So for instance, if we were asking what's the predicted value when x is 6, we're going to get something on the line here that doesn't really represent reality. Same with 10. So this would not give us meaningful results. Our second assumption is that we have no outliers. or we have very few outliers. On our graph on the left, we don't have any outliers, so the line fits very well. Notice how much, and again, these are two similar data sets except with 1 point tweaked. Notice how with this 1 point that's tweaked way out here, that this greatly influences our line of best fit, our regression line. So the 4 points here that used to be underneath our regression line, or used to be above our regression line rather, are now well underneath. In fact, most of our data is well underneath our regression line. So that one outlier is affecting our resulting data or our resulting regression in a big way. And finally, this idea of constant variability. On the graph on the left, we can see that the amount at which the the observed values are off the line, are relatively constant. There's a little bit of fluctuation, but for the most part, the distance between our line and the observed value is around the same. So the variability doesn't change much. On the right, we can see that as we go along the x-axis here, the amount by which we can our observed value varies from our predicted value seems to be growing. Notice how it forms almost like a cone or a funnel shape. That's an indication that you have some sort of inconsistent variability, and in fact that the two variables might be, I believe, collinear. So in other words, we've got some issues here with inconsistent variability, which is going to affect how reliable this regression analysis is. Now, how could you deal with assumption number 3? That suggests that you have other issues with your data. In order to fix this inconsistent variability, you may need to choose different independent and dependent variables. So this may not actually work that well for a regression. You may not be able to trust the results that you get back from it. Let's talk about R-squared, the value of R-squared. So R-squared is a value that's going to range between 0 and 100%. Lower values mean the less our two variables correlate to each other. So if it's 0, then the two values have no correlation with each other. 100% means how much of the variance was explained by our model. So if we have a value of 100%, then we can say 100% of our variance in the data is explained by the model. So in other words, we can say that the variation in our dependent variable is explained by our independent variables. So it explains how well our model actually describes reality. However, that's not the end of the story. There's another value called adjusted R-squared. Because what we can do is we can always improve R-squared by adding more variables. However, they might not improve our model. We might start overfitting our model. Our adjusted R-squared compares the variability we get to chance. So in other words, how well does adding this new variable improve our model versus how just leaving it up to random chance would? So if the variables explain our model better than chance, we're going to get a better adjusted R-squared. It's entirely possible to get a very high R-squared and get a very low adjusted R-squared. So if you get a very low adjusted R-squared, that tells you that the variables that you've added have not added much value to your model. If you want to read on further, there are extra resources that will be listed in the course notes or in the video description below. You can take a look at these. I specifically suggest the interactive tutorial by Powell and Lehe, the problems with least squares by Horber, and finally, all about heteroscedasicity by the Stats Make Me Cry tutorial. Great website, by the way. Enough theory. Let's jump into Python. So last time we left off, we were taking a look at our youth violent crime, and what we want to do is see if the youth unemployment rate has any correlation with violent crime count, homicide count, or theft count. So in other words, is there any relationship? We're going to use unemployment rate as our response variable and our x variable, or our independent variables, will be the violent crime count, the homicide count, and the theft count. Now, the astute among you might say, hold on a second, those sound like violent count, homicide count, and theft count. They might sound fairly similar, because chances are if you're committing some sort of a theft, there might be a violent crime associated with that. And I'll grant you that. For purposes of this demo, let's assume that these are 3 independent crimes, so there's no overlap. First thing we're going to do is read in some unemployment data from Statistics Canada, and we're going to transform that around. Now, this unemployment data has been provided by Statistics Canada, and again, the link to that will be in the video description below. Like any good cooking show, I prepared this data ahead of time. And the way that I've downloaded this data, there is a lot of noise in this data file. And I only really want the unemployment rate because I'm going to join this up based on the fiscal year in a couple of minutes. So what I'm doing is I'm dropping all of the extra columns that I do not need, readjusting these values to be between 0 and 1, and forcing our fiscal year to be strings so that I can join based on fiscal year in a moment. So we're going to combine these 2 data frames. So remember, we created that data combined, which has our 5 crimes indexed by fiscal year and by region. So we will combine these 2 data frames using datacombined.join. So if we combine that, so now we have our datacombined.join, and we've joined it with the unemployment data, and you'll see that I've got 1 extra column here called unemployment rate. Excellent. Now, what does the correlation look like? We could create a quick correlation. Between these 2 and see. So if I do data core equals datacombined.core. And we see that for violent crime and theft, they seem fairly heavily correlated, which is interesting. We see a negative correlation between unemployment rate and violent crime, but it's very small, so not really meaningful. In fact, not really any strong effects here. But let's go ahead and run our regression analysis. Let's see what this looks like. So in order to do this, first off, we're going to specify our response variable to be data combined, and it's our unemployment rate. And then we'll set our x to be our data combined, our independent variables to be our violent crime count, our homicide count, and our theft count. There we go. And then we will add our constant factors, we'll add our constant terms so that we're not forcing this to go through 0. Otherwise, it messes with the model. Then we'll make our model, and we'll set it to SM. Remember, we imported SM up here, Stats Model API. SM.OLS, our independent variable, our dependent variables, and we'll fit that line. And we'll make our predictions by doing model.predict x. So here we go. Let's create our regression model. And let's print out our model summary. So we'll do print model.summary. And this gives us a summary output of our model. Our confidence interval, our t-test, and our R-squared and our adjusted R-squared. Check this out. We have a negative adjusted R-squared, which means that our violent crime count, our homicide count, and our theft count not only explain none of the variability in our model, but explain the variability worse than chance. So should we use this regression model? Absolutely not. This regression model is not useful in the least. We should not use it. Isn't that fascinating? You can have a negative adjusted R-squared. So in other words, this data is being described, this model is describing the data worse than just random chance. So the predicted value of unemployment rate is described worse than if we were to just leave this up to random chance. Fascinating, isn't it? But that's all you have to do to create a regression model in Python. You use the stats model API. We import that as SM, clean up your data frame, set up your dependent variable, set up your independent variables, add your constant term, do sm.ols, independent and dependent variable, dependent, then independent variable, fit that regression line, do your prediction, and run your model summary. Now, what if you wanted to print that out and actually see what this looks like? Well, we can use the pandas plotting library, and we can plot this out. So check this out. I'm going to do pd.plotting.scatterMatrix. And Python will chew on this, and we'll get a whole bunch of really cool graphs, which will show us here's what the data looks like. We see that there's some, looking at this, we've got violent count versus the theft count. We see it's generally a linear relationship. But again, looking at this, there's not, if we look at unemployment rates, say, versus violent count, we see there's almost no relationship. There's nothing really worth looking at here. Isn't that fascinating? So that is ordinary least squares linear regression models in Python. Hope you enjoyed this tutorial, and we'll talk to you again very soon.